guess you need to share them on Slack, right? Okay, perfect.
Okay, whenever you're ready.
All right. Hi, everybody. I have the pleasure of giving the first student talk. My name is Kathrine, and I'll be talking about my project Deciphering cosmic neutrinos. So I work with the very high energy end of astroparticle physics. So that means the high energy neutrinos, the ones I'll refer to as cosmic neutrinos, and then ultra high energy cosmic rays and gamma rays. And as my name might reveal, I'm not only a local in terms of being here from the Niels Bohr Institute, I'm also one of the Danes. So if you want any tips on Copenhagen, feel free to reach out. All right. So as I said, I work with the neutrinos, but in this multi-messenger view. To me, it is one of the most compelling unsolved mysteries in modern physics, as I bet for many others as well, where these ultra high energy cosmic rays and high energy neutrinos come from. We still don't know. So to me, that's extremely exciting. And what is very cool here is that the neutrinos is a very important aspect to include if we want to figure out where these things come from. Because when we see high energy neutrinos, we know that there have been cosmic ray interactions taking place. And also they have this added bonus of actually pointing back to where they came from. So this is the point of multi-messenger physics or multi-messenger astrophysics, that we take all the signals that we get and then we try to squeeze as much information out of them as possible. Because I mean, they're precious, they're expensive, and they're really hard to come by. So might as well make the most of it. So that is why I try to work with all of them and not just the neutrinos. But in this project specifically, the goal is to figure out where does the high energy neutrino flux that IceCube has observed, where does it come from? So of course, there are many different sides to this story, but let's start with looking just briefly at this multi-messenger view, but Futeni already showed it earlier, so I'll just briefly summarize. We have some ultra high energy cosmic rays. In this case, they could be protons. They will propagate through the universe and undergo different interactions with the photon backgrounds we have in the universe. So they'll create these other messengers, gamma rays, that will then cascade into these electromagnetic cascades, and also some high energy neutrinos. In this case, it would be cosmogenic neutrinos, the most high energy ones. But these three messengers that I'm showing here, they all have pros and cons. So the protons or cosmic rays, they're charged particles, so they'll get deflected, as we also heard already. The gamma rays, they'll be absorbed and they'll be re-emitted. The neutrinos, however, will not. They won't get absorbed, they won't get deflected, they'll just point straight back to where they came from because they're weakly interacting particles. I said pros and cons, right? So the con is that they're really hard to catch. So we built gigantic detectors in order to be able to get enough statistics for these high energy neutrinos. IceCube, I'm a member of. The Neutrino Observatory was also introduced earlier by Futeni. But so I'll just briefly mention the scale here. You've probably seen this, or many of you have probably seen this illustration before, where you have the Eiffel Tower and it's supposed to like really get you some intuition for the scale of it. But to make it a bit more local, I've also superimposed it on top of Copenhagen. So as you can see to the left there, to make it even more local, pointed out where we are right now at NBIA, and also stuck in this round tower, which is one of the iconic buildings of Copenhagen. If you go for a little stroll into the inner city, you'll be able to see this. And as you can see, it's only a few pixels out here on the side. So it is really a gigantic detector we need. So what have we gotten out of this? Well, IceCube has detected cosmic neutrinos. That's amazing. But we're in this peculiar situation where at the same time, we still haven't seen any point sources. So that's actually quite remarkable. That means we must have we expect to have some sources of high energy neutrinos that are extragalactic, since they seem to be pretty isotropic, but they must also be kind of weak. Otherwise, we should have seen them, right? So we use this to put constraints on the different source populations that could have caused these high energy neutrinos. And one way to do that is in terms of the density and luminosity. Might ring a bell. We just heard a lot about this earlier. So yeah, you don't have to try to look surprised now. This would be a bit of a repetition of what Futeni already told you. But a slightly different way to do it, let's just look briefly under the hood here, is we've worked with a probability distribution for the brightest source. That would be from some member of some neutrino population, some neutrino source population. And then we consider a simple case first, where we just have a standard candle luminosity function. And then we include the redshift evolution of the sources. So the fact that they could have not evolved at all, been constant, or evolved with a star formation rate and stuff like that. And that allows us to make plots like this, which is, yes, the one you also saw earlier. But there are two important things to note here. There's some blue and there's some magenta. The blue stuff is what we can exclude by having not observed these point sources yet. So that we use, in this case, IceCube's 10-year point source discovery potential, which was also one of the plots that Tina showed you earlier. And the magenta band, on the other hand, is what is actually fixed by what we have seen. Maybe a bit more interesting, that should sort of fix where we expect if we only had one neutrino source population that dominates this measured diffuse flux, it needs to be somewhere in this band. And the reason this band has a width is because of this redshift evolution that I mentioned. So the upper and lower bounds correspond to no evolution or very fast redshift evolution, respectively. All right, but so we can use this to try to put some characteristics on what could these neutrino source populations be. But what if we make that a little bit more realistic? So one way to do that is to consider not just the brightest sources, but also maybe the second brightest, third brightest, etc. So we've derived this probability distribution for the k brightest sources. And then we want to test this just by doing a simple little simulation. We have a lot of individual point sources, and we run that over and over and over. Then we each time collect what was the brightest one, what flux did it have, what was the second brightest. And then we get histograms like this, but since I'm running out of time, I'll just say, whoo, look, great match. Some other ways to improve upon this and make it more realistic is to replace this standard candle luminosity function with something more realistic, and then to go into this non-Poissonian statistical description of what's going on, so that we have a background and a diffuse signal, which we describe with the Poissonian statistics, and then we would have only the Poisson signal itself being something non-Poissonian. But as you can tell by the fact that I've run out of time, this is a work in progress. So this will ideally become something that we test in an IceCube analysis. And then as a next step, we would then also look at what would this mean for the gamma ray flux. So that's all. Thank you.
We have time for like one quick questions, but of course there will also be discussion sessions later if you want to ask questions. Yep.
Really nice. So I'm wondering, first of all, so actually, how can I understand, how does it help you to add these extra sources to your analysis? So if you...
That's a good question. So we haven't, this is still just a work in progress. So we haven't looked that much into it yet. It might not have an effect, but if we, in all these plots so far, they are solely characterized by the brightest or the closest source. So it could have an effect if we could consider not just the brightest, but the second brightest, etc., because then they could show up in these like these small statistical fluctuations that you would have to show a point source signal. But I mean, we haven't done it yet, so maybe it doesn't matter at all. But it's an idea for how to, yeah, if we have something where it's not just dominated by only the very brightest, but maybe we could also see parts of the second brightest. Yeah, so it's a way to start exploring that.
Okay, I won't ask more, but I'll ask later. Thank you.
Thank you. The next talk is by Sunanda.